All right, now the last batch of problems, let me not spoil it here. Use any method to determine if the series converges or diverges. Any method. So throughout this batch of problems, so, by any method, I mean any method that we've talked about. So geometric, telescoping, nth term test, integral test, right? Comparison test. I was trying to think of the other one. Okay. Or, of course, the ratio and root test. All right. So I'm going to talk a little bit about what is it about this particular series that's making me use this test, because that's one of the biggest struggles people have with series. All right, here we go. The sum n going from 1 to infinity of n factorial over 10 to the n. This is a great candidate for the ratio test. The ratio test is great for series with factorials and exponentials, okay? And you're going to see why here in just a second. So use ratio test. The limit as n increases without bound. I'm going to write absolute value and then I'm going to drop it because this series does not have any negative terms. It's equal to the limit as n increases without bound of a sub n plus 1, which is n plus 1 factorial over 10 to the n plus 1. Divided by a sub n, I will multiply by the reciprocal of a sub n. Okay, so 10 to the n over 10 to the n plus 1, we can just cross those out and leave a 10 on the bottom. Now let's talk about n plus 1 factorial over n factorial, because this is a trick that you definitely need to know when it comes to factorials. N plus 1 factorial is equal to n plus 1 times n minus 1 times n minus 2 times every smaller number until you get to 1. In other words, n plus 1 factorial is just n plus 1 times n factorial. All right. And then downstairs we have 10 times n factorial. So it's really useful to be able to separate the n factorial like that, because goodbye, can just get rid of it. So we're left with limit as n increases without bound of n plus 1 over 10. As n increases without bound, so does n plus 1 over 10. This limit is infinite. This series diverges. All right, on to letter B. The sum n going from 1 to infinity of the nth power of negative 2 over 3 to the n. Well, you could use the ratio test for this. You could use the root test for this. But this is actually a geometric series, because when n equals 1, this is negative 2/3. When n is 2, this is negative 2/3 to the second. When n is 3, this is negative 2/3 to the third. Okay, so I mentioned to you a little while ago that when we were talking about the root test, when everything is to the nth power, that is a cue that the root test would be good. But I also mentioned that there are some specific circumstances under that where the geometric series is even easier. Okay. This is a geometric series because both of those bases, the negative 2 and the 3, are constant. All right, so this is geometric. To get from one term to the next, you're always multiplying by negative 2/3. R is negative 2/3. The absolute value of R is less than 1. This series converges. And we could even say what it converges to, but they didn't ask. So moving on. All right, letter C, the sum n going from 1 to infinity of the nth power of 1 minus 1 over 3n. All right, this, it turns out, is a good candidate for the nth term test. The nth term test is a good one to try when you think that the limit of the nth term might not be 0. And remember, that's the only situation where the nth term test works. So as a reminder, the nth term test says that if a sub n is not approaching 0, then the series diverges. This is the one you have to be careful with because the converse is not true. If a sub n is approaching 0, the test is inconclusive. Okay, you have to use something else. So I use the nth term test when I have an inkling that that nth term might not be approaching 0. So let's look at the limit of that nth term. And I am going to take a little shortcut here, but I will explain how to do this the long way if you didn't have this shortcut handy. This limit, it turns out, is equal to e to the power negative 1/3. And the reason I know that is by theorem 5 in section 10.1, number 5. Let me put that on the screen for you real quick. Okay, this is the theorem that I am referring to from section 10.1, looking at number 5. The limit as n increases without bound of 1 plus x over n to the power n is equal to e to the x for any x. So in the problem that we are working on, x is equal to negative 1/3. So again, if you didn't have that theorem handy, the way that you could do this the long way is the way we talked about before. Let L equal the limit as n increases without bound of 1 minus 1 over 3n to the n. And look at the natural log of L, that trick. Okay. All right, but the important thing about this limit, e to the negative 1/3, is that it is not 0. And because that limit is not 0, this series diverges. All right, last example. Oh, doesn't this look fun? The sum n going from 1 to infinity of 1 times 3 times 5 times ... all the way up to 2n minus 1 divided by 2 times 4 times 6 times ... times 2n times 3 to the n plus 1. All right, so I need to show you another trick. And it's for making these, I like to think of them as odd and even number factorials. So let's start with the even number factorial. 2 times 4 times ... times 2n. All right, what I'm going to do is break a factor 2 off each of those. So if I removed a factor 2 from each of those, I'd be left with 1 times 2 times 3 times da 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 up to n. And how many factors of 2 did I break off? I broke off n factors of 2. So that means I could put a 2 to the n in front, okay? So the even number factorial can be formed by taking 2 to the n times n factorial. All right, so now let's talk about the odd number factorial. 1 times 3 times 5 times da 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 times 2n minus 1. Got noisy birds in the background. Okay, so what I'm going to do with that is I'm going to put all of the numbers from 1 to 2n upstairs. And then I'm going to divide out the even factors that I don't need. See that? So after I cancel out the even factors, only the odd factors would be left. So upstairs, you have the factorial of 2n. And downstairs, you have the even number factorial, which we just talked about, is 2 to the n times n factorial. Okay. All right. So now we have everything we need to rewrite this series in a form that I can do something with it. Okay, so we have the sum n going from 1 to infinity. 1 times 3 times 5 times da 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 up to 2n minus 1 over 2 times 4 times 6 times da 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 up to 2n. And then over here we have this 3 to the n plus 1. Okay, so what we know now is that we can write the odd number factorial as 2n factorial divided by 2 to the n times n factorial. And we can write the even number factorial as 2 to the n times n factorial. And then we have this 3 to the n plus 1. Okay, so this looks to me like it's going to be a candidate for the ratio test. So now what we should do is, before we use the ratio test, let's simplify this complex fraction by multiplying the top and the bottom by 2 to the n times n factorial. Okay, so we say goodbye to that, and we say goodbye to that. And what we're left with is 2n factorial over 2 to the n times 2 to the n, which is 2 to the 2n, or I could write it as 4 to the n, times n factorial times n factorial times 3 to the n plus 1. Whew. Okay, all that work just to write it in a form where we can do something with it. All right, so now let's use the ratio test. The limit as n increases without bound of absolute value a sub n plus 1 over a sub n. And again, I do not need the absolute values. All these terms are positive. Okay, now I need to be careful here. A sub n plus 1 is going to be the factorial of 2 times n plus 1. See how I'm doing that? Over. Whoops. Okay. 2 to the power 2 times n plus 1 times n plus 1 factorial times n plus 1 factorial times 3 to the power 2, 3 to the n plus 1, add 1, Okay, that's just a sub n plus 1. And now I have to divide by a sub n. How am I going to squeeze this in here? Well, it's going to be 2 to the 2n times n factorial, 3 to the n plus 1 over the factorial of 2n. Okay. All right, so the good news is we're going to be able to get rid of a lot of this stuff. Let's see. Well, n factorial over n plus 1 factorial, we did something like that before. You can cancel those and just leave an n plus 1. And the same thing here. Now, let's look at 2 to the 2n and 2 to the power 2 times n plus 1. Would it be okay if I do this? Let's rewrite this as 2 to the power 2n plus 2. And then using properties of exponents, 2 to the 2n divided by 2 to the power 2n plus 2 is just going to leave 2 to the second downstairs. Okay. All right, almost done. Let me rewrite the factorial of 2 times n plus 1 as 2n plus 2 factorial. So I'm looking at this and this. And off to the side, let me just point out that the factorial of 2n plus 2 is 2n plus 2 times 2n plus 1 times 2n all the way down to 1. So in other words, times the factorial of 2n. All right, so in other words, you can divide this into this, and it's just going to leave 2n plus 2 times 2n plus 1. Okay, so what's left? Looks like 2n plus 2 times 2n plus 1 times 3 to the n plus 1 over 2 to the second times n plus 1 squared times 3 to the power n plus 1, add 1. Okay. So I am going to, well, this part right here is a rational expression. The leading term upstairs is 4n squared. The leading term downstairs is 4n squared. That part of the expression is going to go to 1. Okay. Now I'm going to say something and I'm going to leave it for you to fill in the details. Let's talk about 3 to the n add 1 divided by 3 to the n plus 1 add 1. If it weren't for those plus 1s, hopefully it's clear that that limit would be 1/3, right? Well, I claim that it's still 1/3 even with the plus 1s. All right. If you're not convinced, you can use L'Hopital's rule on that part of it. The plus 1s will disappear in the first step. And you should be able to show that that the limit of that part is 1/3. All right, so there you have it. That limit is 1/3. What was the question again? Oh, the question was, does the series converge? We were using the ratio test. 1/3 is less than 1. This series converges. In fact, it converges absolutely, but they only asked whether it converges, so that's what we will answer. And that's going to do it for section 10.5. We'll see you next time.